Hello friends, I am Dr. Manisha, Assistant Professor from KVN Naik College, Nasik. Friends, we have started the series of lectures. In the previous video, you have seen that we have started Optics SYBSc Physics Paper 2nd. In that, we have started lens aberration. In the previous video, we have seen the different types of monochromatic aberration and we have seen spherical aberration in detail. In this today's video, we'll study the second type of aberration, that is coma. Friends, if the point object is situated off the principal axis, the lens forms a comet-like image in place of point image. This type of defect in the image is called as coma. Now, this figure illustrates the presence of coma in the image due to the point object situated off the axis of the lens. In order to understand the chromatic aberration produced by the lens, consider the rays of light originating from this point A and passing through the various zones, that is 1 1, 1 2, sorry 2 2, 3 3, etc. of the lens. Now the rays of the light originating from point A and passing through the zone limited by the rays 1 1. Then in this figure we can see meet the screen XY at point P, and the screen XY is placed perpendicular to the axis of the lens and at that position where the central rays come to focus. Now the rays originating from point A and passing through the zone limited by the rays 2 2 meet the screen at point Q, and the point Q is little in front of focal plane XY. This is due to the fact that the lens has shorter focal length for the non-paraxial rays, isn't it? This is the defect. Now the cone of the rays start from point A and inclines as the rays 2 2 will meet at point Q. Now if now the screen is placed at XY, the cone will produce the bright circle on the screen, and the diameter of this circle depends on the distance of the point Q from the plane XY. Now considering the joint effect of various zones of the lenses, the overall image of the point object can be said to consist of the series of circles, isn't it? Now the radius of the circle increases with the increase of the radius of the zone of the lens. Now all these circles are found to overlap, resulting in an image having the appearance of a comet-like shape with its tail towards the point P, fine, and the head towards F. Now the intensity of this comet is greater at point P and decreases as it approaches to F. Now due to this appearance of the comet, the defect is known as coma. Now we have to reduce it again. So here are the different types or the methods to reduce this coma. Now we have seen that the chromatic aberration arises due to the variation of the lateral magnification for the rays passing through the different zones of lenses. The chromatic aberration can be eliminated by the different methods. First one is like spherical aberration. Chromatic aberration can be produced by the single lens, can be reduced by the suitable choice of the radii of curvature of the lens surfaces. For example, for the object situated at infinite distance from the lens, the chromatic aberration can be minimized by using the lens of refractive index mu is equal to 1.5 and R1 upon R2 is equal to minus 1 upon 9. Now, coma can be minimized by using the stop or the diaphragm at the proper positions. Then it also eliminated if each zone of the lens satisfies the Abbe sign condition. What is it? It is mu1 y1 sin theta 1 is equal to mu2 y2 sin theta 2. Fine. Mu1 and y1 and theta 1, they refer to the refractive index, height of the object above the principal axis, and slope of the angle of incident ray of the light respectively. Now the quantities mu2, y2 and theta 2, they refer to the refractive index, height of the image and slope angle of emergent rays of light in the image medium respectively. Now the lateral magnification of the lens is given by y2 upon y1. Fine. So lateral magnification y2 upon y1 is equal to mu1 upon sin theta 1 upon mu2 upon into sin theta 2. Now, if the lateral magnification y2 upon y1 is same for all the rays of the light irrespective of the slope angles, that is theta 1 and theta 2, then coma may be eliminated. Since mu1 upon mu2 is constant, coma will be eliminated if sin theta 1 upon sin theta 2 is constant. So the lens that satisfies this condition is called as aplantic lens. Okay, and the corresponding surface is an aplantic surface, and the phenomenon as a whole is called as aplantism. Then next type of aberration is astigmatism. Now, when the point object is situated far off the principal axis, its image consists of two mutually perpendicular lines separated by the finite distance and lying in the perpendicular planes. This type of defect of the image is called as astigmatism. Now, see in this figure, the presence of it shows the presence of astigmatism. Now, the point object O, it is situated far off the axis of the lens. Even if we consider the small aperture ABCD of the lens near the center, we find that due to the large inclination of the rays with the axis of the lens, all the rays originating from O after refraction through the lens do not meet at the single point. Correct? So the image of the point object O consists of two mutually perpendicular lines PP dash and QQ dash, which are separated by the finite distance. Now the plane passing through the point O and the principal axis is called as tangential plane, and the plane perpendicular to the tangential plane and passing through the principal axis are called as sagittal plane. Now, see in this figure, ray OA and OD are in tangential plane. Similarly, the rays OB and OC are in the another tangential plane. The rays OA and OD are refraction through the lens meet at the point P. Similarly, the rays OB and OC after refraction through the lens meet at point P dash. So, intermediate pairs of tangential rays meet at points between P and P dash, and P dash is the line image of the point object O, and the rays OA and OB are in one sagittal plane. These rays after refraction through the lens meet at point Q dash. Similarly, the rays OD and OC are also in one sagittal plane. These rays after refraction through the lens meet at point Q. Intermediate pairs of sagittal rays meet at point QQ dash. Thus, QQ dash is another line image of point object O, and the line images PP dash and QQ dash are called as tangential image and sagittal image of the point object O respectively. Now, the image of the point object consists of two mutually perpendicular lines PP dash and QQ dash, which are separated by the finite distance and lying in the perpendicular planes. This defect of the image is called as astigmatism. Fine. The distance between the PP dash and QQ dash along the principal axis is called as astigmatic difference. Now we have to reduce it again. So here are the different methods to reduce the astigmatism. The defect astigmatism can be reduced by the defect arises due to the large inclination of the rays with the axis of the lens. Therefore, if the rays making the angles larger angles with the axis of the lens are cut off by placing the stop arrangement in the proper position, the lens may be corrected for the defect of astigmatism. The distance between two line images along the principal axis in the convex lens is opposite direction to that by the concave lens. Therefore, by using the suitable combination of convex and concave lens, astigmatism aberration can be minimized. Now, for the optical system consisting of the several lenses, the defect of astigmatism can be reduced by adjusting the respective positions of the lenses. So, these are the different methods to reduce the astigmatism. In the next video, we'll see the other types of aberrations, that is curvature of field and distortion. Thank you.